Hello, good morning students. Today we discuss about the formation of stationary waves in a stretched string. From that we deduce the laws of transverse waves. Before going to that, first we have to know what is waves. A wave is nothing but disturbance created in the medium, and that disturbance is propagate through the medium and transfer energy and momentum along with it. That these waves are of two types: mechanical waves and electromagnetic waves. Mechanical waves ante the waves which requires medium for their propagation are called mechanical waves antaru. That means for the propagation of these waves they require medium. Example వచ్చేసి sound waves, water waves, waves produced in a string. These are mechanical waves. For the propagation of these waves they require medium. అలా కాకుండా the waves which do not require medium for their propagations are called electromagnetic waves antaru. For the propagation of these waves they won't require any medium. Example for these electromagnetic waves are light waves. Here the light, we receive light from the sun and there is no medium between sun and earth beyond a certain height. And these waves are again two types. One is progressive waves and stationary waves. Progressive waves ante the waves which are produced in the medium propagate through the medium continuously until its energy is exhausted. And these waves, these progressive waves carry energy from one place to another place. Whereas in stationary waves, the energy is stationary in between two rigid supports. The energy is stationary in between two rigid supports. That's why these waves are called stationary waves antaru. And we know that the progressive wave equations are, for example, if a wave start with crest and move towards the positive x direction, then the wave equation is given by y equal to a sin omega t minus kx. Y equal to a sin omega t minus kx, where y is the displacement of the particle at any instant and a is the amplitude of the vibrating particle of the medium, and omega is the angular frequency, and k is the propagation constant, where k equal to 2 pi by lambda, and x is the distance of the vibrating particle from the rest position, the mean position. From the beginning. అలా కాకుండా suppose if a wave start with trough and move towards positive x direction, then the wave equation is given by y equal to a sin kx minus omega t. Y equal to a sin kx minus omega t. అలాగే similarly, if a wave start with crest and move towards negative x direction, then the wave equation is given by y equal to a sin omega t plus kx, లేదా kx plus omega t. These are the equations of a progressive wave. Now we discuss about what is a stationary wave, how stationary waves are formed in a stretched string. Stationary wave. The stationary waves are formed in such a way that when two waves having same amplitude and wavelength travel through the same medium along the same line in opposite direction and superimpose with each other and form a resultant wave pattern called stationary wave antaru. When two waves having same amplitude and wavelength propagate through the medium along the same line in opposite direction and superimpose to produce a resultant wave pattern called stationary wave. Now let us consider, now we are going to explain the formation of stationary waves in a stretched string. Now let us consider a string of length L which is stretched between two rigid support. A string of length L which is stretched between two rigid support. Whenever this string is plucked perpendicular to its length, when the string is plucked perpendicular to its length, a transverse wave pulse is produced. A transverse wave pulse is produced. This transverse wave pulse travel in either direction along the length of the string and get reflected from the rigid support. Reflected from the rigid support. This is the reflected wave. This is the reflected wave. This incident wave and reflected wave both are having same amplitude, same wavelength and travel in opposite direction and superimpose with each other and forms the stationary wave. Now the displacement of the two waves is y1 equal to, this is the incident wave and this is the reflected wave. The displacement equation of this incident wave is given by y1 equal to, here the wave start with the trough and move towards positive x direction. Then the wave equation is y1 equal to a sin kx minus omega t. Kx minus omega t. And this is the reflected wave. Here the wave start with the crest and move towards negative x direction. Then its wave equation is given by y2 equal to a sin kx plus omega t. Y equal to a sin kx plus omega t. Here these two waves undergoes superposition. According to principles of superposition of waves, the resultant displacement is given by y equal to y1 plus y2. Y equal to y1 plus y2. Then y equal to y1 a sin kx minus omega t plus y2 a sin kx plus omega t. A sin kx plus omega t. From this y equal to, if we make a as common, this sin a minus b, this is of the form sin a minus b. Sin a minus b is sin a cos b minus cos a sin b. According to that, sin a sin kx cos b cos omega t minus cos a sin b, cos a sin b, plus again this is sin a plus b. Sin a plus b ante sin a cos b plus cos a sin b. This is a and b. So sin a sin kx cos omega t plus cos a cos kx sin b sin omega t. Here minus cos kx sin omega t plus cos kx sin omega t gets cancelled. Here sin kx cos omega t plus sin kx cos omega t ఏమవుతుందంటే 2 sin kx cos omega t అంటే 2a sin kx cos omega t. Y equal to 2a sin kx cos omega t. This is the resultant displacement of the stationary wave form. Resultant displacement of the stationary waves. And when two waves are superimposed with each other, the resultant displacement of the resultant wave pattern formed is y equal to 2a sin kx cos omega t. Here this equation is of the form y equal to a cos omega t. Y equal to a cos omega t, where a is the resultant amplitude of the stationary wave formed. Here 2a sin kx, Here 2a sin kx is the resultant amplitude of this stationary wave pattern is 2a sin kx cos omega t. Here 2a sin kx is the amplitude of this resultant wave. Here this amplitude is not constant. It depending upon the x value. Here 2 is constant, a amplitude is constant, k propagation constant, but x distance is not constant. Distance is not constant. It changes from as we move from this point to this point, this x value changes. Okay, here this is 0. This is one wave. Trough and crest is lambda. Automatically this will become lambda by 2. Here this will become lambda by 4. This is 3 lambda by 4, 5 lambda by 4, and so on. Now if you observe this one, at x equal to 0, at x equal to 0, then if you substitute x equal to 0, sin 0, 0. So the resultant amplitude becomes 0. Alage from this equation, at x equal to lambda by 2. Lambda by 2 means 180 degrees. Sin 180, again 0. So the resultant amplitude becomes 0. Alage 2 lambda by 2. 2 lambda by 2 means 360 degrees. Sin 360, 0. Sin 360, 0. So again the resultant amplitude becomes 0. That means from this expression, at x equal to 0, lambda by 2, 2 lambda by 2, 3 lambda by 2, and so on, the resultant amplitude becomes 0. The resultant amplitude becomes 0. These points on the stationary wave where the resultant amplitude becomes 0 are called nodes. Similarly, suppose at x equal to lambda by 4. Lambda by 4 means 90. Sin 90, 1. Sin 91 annappudu resultant amplitude becomes maximum. Lambda by 4, 3 lambda by 4. Again 3 lambda by 4 means 270. Sin 270 minus 1. Here minus indicates in opposite direction, but magnitude is maximum. Again the amplitude becomes maximum. That means at x equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, 7 lambda by 4, and so on, the resultant amplitude becomes maximum. The resultant amplitude becomes maximum. These points on the stationary wave where the resultant amplitude becomes maximum are called antinodes. Antinodes means the points in the stationary wave where the resultant amplitude becomes maximum are called antinodes. That means in the stationary wave, nodes and antinodes are formed. Nodes and antinodes are formed. Here the distance between two successive nodes is lambda by 2. Similarly, the distance between two successive antinodes, and 3 lambda by 4 minus lambda by 4, that equal to 2 lambda by 4, that equal to lambda by 2. That means the distance between two successive nodes or antinodes is lambda by 2. Whereas the distance between two successive, like the consecutive node and antinode is lambda by 4. The distance between two successive node and antinode is lambda by 4. Now here this is called stationary wave or standing wave because now we know that the wave carry energy along with it. Now this wave carry energy along with it. Again it get reflected. Again the energy start moving in the opposite direction. Again it get reflected. Again it start moving in this direction. Like that, the energy is stationary in between two rigid supports. It is not transmitting from one place to another place. It is stationary in between two rigid supports. That's why this is called stationary wave. This is called stationary wave. Now whenever a stretched string is vibrated, whenever a stretched string is vibrated, it vibrates with different frequencies and form different stationary wave pattern That means whenever the string is plucked, it vibrates with certain frequency and form a stationary wave like this, or it forms a stationary wave like this, or it forms a stationary wave like this. This forms stationary wave like this. That means whenever a stretched string is plucked, it vibrates with different frequencies and forms different stationary wave patterns. These different modes of formation of stationary waves is called harmonics అని అంటారు. Harmonics. The harmonics with the minimum number of nodes and antinodes are called first harmonic or fundamental harmonic అంటారు. First harmonic or fundamental harmonics. First harmonic or fundamental harmonic means the harmonic with minimum number of nodes and antinodes are called first harmonic or fundamental harmonics అంటారు. And the harmonics other than fundamental harmonics are called overtones అని అంటారు. That means second harmonic or first overtone, third harmonic or second overtone, fourth harmonic or third overtone, like that. Now first fundamental harmonic. The fundamental harmonic, the first harmonic contains minimum number of nodes and antinodes. We know that at the rigid support always a node is formed. In between two nodes it contains one antinode. So the fundamental harmonic is formed like this. Here L is the length of the string. Whenever the string is plucked, it forms stationary wave like this. Then it is called fundamental harmonic because it contains minimum number of nodes and antinodes. This L value is equal to the distance between these two nodes. Now the distance between two nodes is lambda by 2. From this lambda equal to 2L, and we have V equal to nu lambda, speed of wave, V equal to nu lambda. From that nu equal to V by lambda. Therefore the first harmonic frequency, the fundamental harmonic frequency is given by nu1 equal to V by lambda. Here lambda is 2L. Nu1 equal to 1 by 2L into V is the speed of transverse wave in a stretched string. We know that the speed of transverse wave in a stretched string is root of T by mu, where T is the tension in the string, and mu is the linear density of the string, the linear mass density of the string. This is the fundamental harmonics. Whereas the second harmonic, the first overtone, contains one more node and antinode than that of first harmonic. In the first harmonic it contains two nodes and one antinode. So the next harmonic contains three nodes and two antinodes. Okay, second harmonic, the first overtone contains one more node and antinode than that of the fundamental harmonics. From this, and in the same length, the stationary wave may form like this. Then L equal to L is equal to the distance between these 2 points. So distance between these 2 points, this is node. The distance between two nodes is lambda by 2. Again between these two, lambda by 2, that equal to 2 lambda by 2. That implies lambda equal to 2L by 2. Now we have the frequency nu equal to V by lambda, and the first overtone frequency, the second harmonic frequency is given by nu2 equal to V by lambda, that equal to V by lambda means here lambda is 2L by 2. 2L by 2. From that nu 2 equal to 2 into 1 by V by 2L. 2 into V by 2L. Nu 2 equal to 2 into 1 by 2L root of V. V is the speed of transverse wave, me T by mu. T by mu. This is the second harmonic, లేదా first overtone frequency. Again from this nu 2 equal to 2 into what is 1 by 2L root of T by mu. This is the first harmonic frequency. So nu 1. Therefore nu 2 equal to 2 nu 1. Nu 2 equal to 2 nu 1. Next, the second overtone, the next harmonic contains one more node and anti-node than that of the first overtone. The second harmonic. Second harmonic kanna third harmonic lo one more node and anti-node is more. That means in the second harmonic it contains 3 nodes and 2 antinodes. Automatically in the third harmonic or second overtone contains 4 nodes and 3 antinodes. 4 nodes and 3 antinodes. In the same length, okay, this is the third harmonic or second overtone. It contains 1, 2, 3, 4 antinodes, so 4 nodes and 3 antinodes. 3 antinodes. From this, L equal to node to a node distance lambda by 2 plus lambda by 2 plus lambda by 2. Totally 3 lambda by 2. From that, lambda equal to 2L by 3. 2L by 3. And the third harmonic frequency, the second overtone frequency is given by nu 3 equal to V by lambda. V by lambda means 2L by 3. 2L by 3. From that, nu 3 equal to 3 into V by 2L. Nu 3 equal to 3 into 1 by 2L into root of T by mu. This is the third harmonic frequency. Third harmonic frequency, like the second overtone frequency. Or from this, nu 3 equal to 3 into 1 by 2L root of T by mu is the first harmonic frequency. So 3 nu 1. The first harmonic frequency is nu 1. Second harmonic frequency, first overtone frequency is 2 nu 1. Third harmonic frequency is 3 nu 1. Similarly, the fourth harmonic frequency is nu 4 equal to 4 nu 1. And the fifth harmonic frequency is given by nu 5 equal to 5 nu 1. Hividanga we can obtain the higher order harmonics. And their harmonic frequencies are in the ratio. Their harmonic frequencies are in the ratio nu 1 is to nu 2 is to nu 3 is to nu 4 is to and so on equal to nu 1 is to nu 2 means 2 nu 1 is to 3 nu 1 is to 4 nu 1 is to and so on. The nu 1 gets cancelled and their frequencies are in the ratio 1 is to 2 is to 3 is to 4 is to and so on. 1 is to 2 is to 3 is to 4 is to and so on. That means in the formation of stationary waves in a stretched string, the harmonic frequencies are in the ratio 1 is to 2 is to 3 is to 4 is to and so on. Now we know that next వచ్చేసి laws of transverse waves. Laws of transverse waves. Laws of transverse waves. The first harmonic frequency is given by nu equal to 1 by 2L root of T by mu. The first harmonic, and whenever the string is vibrating with the first harmonic, like the fundamental harmonic, its frequency is given by nu equal to 1 by 2L root of T by mu. Mostly, for example, if you take the Venus having a string, whenever the string is plucked, it will vibrate with the first harmonic frequency. fundamental mode లో వచ్చేసి వైబ్రేట్ అవుతుంది. And this first harmonic frequency reduce from this first harmonic frequency we can deduce the loss of transverse wave. Here nu is the fundamental frequency, L is the vibrating length of the string, and T is the tension in the string, and mu is the linear density of the string. From this there are three laws of transverse waves. This is first law is when tension and linear density kept constant, when tension in the string and linear density kept constant, the fundamental frequency is inversely proportional to the vibrating length of the string. When tension and linear density kept constant, the fundamental frequency is inversely proportional to the vibrating length of the string, or nu into L equal to constant. This is the first law of transverse wave. From this, if the frequency is less, the vibrating length is more. If frequency is more, vibrating length is less. This is first law. Next one is the second law. The second law states that when the vibrating length and linear density kept constant, when vibrating length and linear density kept constant, the fundamental frequency is directly proportional to the square root of tension in the string. The fundamental frequency is directly proportional to the square root of tension in the string. If the tension is more, automatically the frequency is more. If tension in the string is less, the frequency is less, or nu by root T equal to constant. This is called second law of transverse wave. The next one is the third law. The third law states that when the vibrating length and linear density kept constant, and the vibrating length of the string and tension in the string kept constant, when the vibrating length and tension in the string kept constant, the fundamental frequency is inversely proportional to the square root of linear density of the string. That means if the linear density is more, frequency is less. If linear density is less, frequency is more. From this, nu into root mu equal to constant. This is called third law of transverse wave.